Okay, good afternoon. So I have still a little bit of pain in my leg, so I cannot stand. So let me just teach you using this. And of course, we also need GeoGebra. Let us try to see if I can concentrate to do everything on the iPad, including recording as well. So today we want to talk about a very important topic, and that's the topic of vectors. Hello. Yeah, please listen. Okay. So what is a vector? First of all, to motivate you, we have two types of quantities, for example, in physics. Yes. For example, if I ask you what the temperature is, you just give me a number. For example, you say that the temperature of the room is 23 degrees. That's it. So the information that you just transfer to me by that number is enough for knowing the temperature of the room at a point. Yes. But for example, if you ask me, okay, Bobak, this place from your place 1 meter, then depending in which direction I am going to take this step, I will end up at different points. So here, just giving me a number, for example, 1 meter for the displacement is not enough. I need also another thing to make it clear where I will end up if I displace from my place 1 meter. If I displace from my place that I'm standing, for example, 1 meter to the right, I end up 1 meter to the right. If I do the same one step, 1 meter to the left, I will end up at a different point. Is that clear? So it means that the displacement is a quantity, of course, but just giving me a magnitude or a number is not enough to specify the whole concept of displacement. I not only need a magnitude, I also need a direction. Is that clear? Yes or no? So this is the difference between these two quantities. The temperature, no one asks temperature in which direction. Yes, that is nonsense. I just tell you that what the temperature is. And that's enough. That's enough for you to understand the temperature. But if I ask you to displace from your place 1 meter, you might ask me in which direction should I take this 1 meter, yes? So the quantities which also depends on magnitude, the quantities which are clear only by giving you a number are called scalar quantities. Scalar. And the other quantities that you also need to know the direction are called vector quantities. Okay? So, for example, can you tell me another scalar quantity in physics, for example? Temperature was a quantity which was a scalar. Can you imagine other quantities that are also scalar? Yes, Haya? Pardon? Technically, weight is not correct, but mass is correct. Technically, in physics, there is a difference between mass and weight. Yes? So let us take this for granted for the time being. Yes, mass is a scalar quantity. Yes, because you say that what is the mass of something, you say that the mass of this thing is 2 kilograms, for example, and that's it. Yes, you don't talk about the direction of the mass. Another scalar quantity, can you imagine? Yes, please, Tim? No, again, velocity is not. A speed. These are technical differences from physics and mathematics. A speed is a scalar quantity. A speed is exactly what is shown by the speedometer of the car. The speedometer of the car, if you are driving 60 kilometers per hour, that is 60 kilometers per hour. It doesn't depend. Are you driving to the north? Or are you driving to the south? Yes, both of them. Thank you, Sergey. Thank you. Yeah, it's already locked. Yeah, when you close it, it's already locked. Thank you. So, a speed is a scalar quantity, but velocity is the. Pardon? Yes. No. When you say speed, the number is enough. When I talk about velocity, I not only should give you the magnitude of the velocity, which is a speed, but I should tell you in which direction. For example, if I say the speed of the car is 60 kilometers per hour, this sentence is complete. But if I tell you the velocity of the car is 60 kilometers per hour, the audience should be waiting for the rest of the sentence. You should say the velocity of the car is 60 kilometers per hour due north. So when you use the word velocity, you should also specify the direction, not only the speed. So that is exactly a very good example that Tim actually brought up. So speed is a scalar, but velocity is a vector quantity. Yes, is that clear? So what is probably the most famous vector quantity, as I said, probably is displacement. Yes. What is the English word for the magnitude of the displacement? Yes? Length or distance. Yes? So distance and displacement are two different type of quantities. Distance is a scalar quantity. I ask you, what is the distance between Stockholm and Malmö, for example? Yes? So this distance is a scalar quantity. But displacement is a vector quantity. So if I tell you that the displacement is 2 meters, it's not clear. You need to also specify the direction. Yes, is that clear? Okay, so another famous vector quantity probably is, it's very famous one. Yes?
I was thinking scalar force.
Yeah, it's a scalar. A scalar is not so exactly. Force is a vector quantity. So your answer is correct. I was thinking about force as well. For example, if you look at this AirPod case, so if I push it in this direction, it will go in this direction. If I use the same amount of muscular energy or strength and do it in this direction, it will go in the other direction. So the place that the direction that this will move depends on the direction that I am exerting the force, not only the magnitude. Yes? So this is just, if I want to summarize, there are two very important types of quantities in physics. One of them is scalar quantities, and the other one is called vector quantities. Yes, and that's the difference between these two. So for vector quantities, we also need a direction. Any questions so far? No? Okay. So now in mathematics, a vector should also have the same attitude. Yes. So what is that? We need, if we want to denote a vector in mathematics, what we do, we actually, so I would say that, let me write a definition here for you. So definition, a line segment equipped with a direction is called a vector. Yes, so for example, if I start from here to here, that's it, then this is just a line segment. Yes, for example, let me give these points a name, point A, point B. So these 2 points are the end points of this line segment. As soon as I put an arrow here representing the direction, then this object that you see here is called a vector. And this point A is called the initial point. Yes, I can write it down here for you. So here, this point is called the initial point. And this point B is called the final point. And in total, if I want to denote this vector, I write it in this form. I write AB, and then I put an arrow on top of that. And it is extremely important to write A first and B second. Yes, when you are dealing with a line segment, it doesn't matter if I just want to denote this line segment. It doesn't matter if I call it line segment AB or if I call it line segment BA. Both of them, by convention, refer to the same line segment. But when I am dealing with vectors, it's extremely important. First of all, you shouldn't forget to put this small little arrow on top of that. And this is extremely important to start with the initial point and then end with the final point. The final point is the point containing this tip of the arrow. Yeah, so that is called a vector. But of course, usually we do not care about the initial and final points. What we care is just the vector itself. So in those cases, what we can do, we can put a symbol letter, for example, V, and equip it with that one. So I would say that there are two different ways to denote this vector. Either you can call it vector AB, or you can call it simply vector V by putting a V on it. Yes? And usually it doesn't matter if you put V here, some books put the V here, it doesn't matter. Yes? So if the initial and final points are important, we have to use this symbol. If the initial and final points are not that important for us, we just use a symbol like that to denote it. Yes? Any questions? So that is the official definition of a vector. You can do that, but that would be another vector. It is not the same vector. Yes? So for example, if you are asking, if I put the tip of the arrow here, then this will be called the final point. This will be called the initial point. But if you want to write the symbol for it, you have to write BA vector. Yes? So that's important. So you have to respect the order here. Is that clear? Okay. So one thing that I want you to know is the zero vector. This also needs definition, the zero vector. So the zero vector is denoted by this symbol, like O, and you put an arrow on top of that. So what is the zero vector? Any vector whose initial and final points coincide is called the zero vector. Yes? So that is, the zero vector is just single point. Yes? So if I ask you, for example, if I ask you what can I write instead of AA? What can I write instead of AA? This is the zero vector, because this is the vector whose initial point is A and its final point is also A. So by definition, this is just the zero vector. Okay, if I ask you what is BB, then what is your answer? What is this vector then? Yes? That is the zero vector again. So you see, for the zero vector, we can write different names, yes? So I would say that, so let me write this as a remark. So if someone asks you what is the definition of the zero vector, you would say every vector whose initial and final points are the same is called the zero vector. Yes, but so I would say that let x be an arbitrary point then, so I want you to remember x as a vector is nothing except a zero vector. Okay, so that is good to know. Okay, so something that I want you to know, of course, there is nothing here to prevent me from measuring this length. Yes, I can take my ruler and measure the length of the vector. Yes, Okay, so that is just a length. So the length of the vector is denoted by this. So the length, there are different names for the length. The length, some more advanced books call it norm. This is not usually used in high school. Or sometimes we say magnitude. Of course, magnitude is also good. Of a vector is the length. So of a vector, let me write it in this way. The length of a vector AB is the length of the line segment AB. Okay, so the norm of a vector is denoted, and it is denoted, let me write it here, and it is denoted by this symbol. You have this symbol, you see, or of course I myself prefer to write it in that way. I prefer the second one. It's a little bit more complicated to write because this is also a little bit more, this is another symbol that we use in mathematics, and that's the absolute value. So of course there is no matter of confusion. Absolute value is not something hard. So when I say the absolute value of a number, I mean its magnitude. So if I ask you what is the absolute value of 2, you would say 2. If I ask you what's the absolute value of -2, the answer is again 2, even though -2 is negative, but the magnitude, from magnitude point of view, the magnitude of -2 is also 2, yes? So this is why this symbol is ubiquitous in algebra, but there is no matter of confusion here, because inside this you see a vector, but inside the normal absolute value you see a number. So you will never ever confuse this symbol with that symbol. But anyway, some books or more advanced books write the magnitude of a vector by these lines. So for example, here, if I go and ask you what is the magnitude of vector v, how should I do that? I will take my ruler and I will measure this, whatever it is. For example, it is 10 centimeters, for example. Then I would write this is equal to 10 centimeters. Yes? So remember that v, the vector v, is a geometric object, but the norm, the magnitude, or the length, there are three different words for the same thing. This is a number. What type of number do you think it is? Yes, Rasmus? Yeah, exactly. That's a very good thing. I didn't mean that, but that's correct. You are saying that even though v is a vector, the magnitude of the vector is a scalar. Yes, that is correct. But I mean, what type of number is it? Is it a natural number? Is it a negative number? Is it a complex number? What it is? What? No. Why natural? For example, can't you imagine a vector of length 2.5 centimeters? You can imagine, yes, but you cannot imagine a vector of length -5. It doesn't make sense, yes? So can you tell me what type of numbers are allowed for the magnitude of the vector? Yes, and with one more exception, yes, positive and real, positive, real, and no, because you know that might be, I don't know. Do you know if I ask you 0, is number 0 positive or negative? What is your answer? Neither of them. So this is I don't know how many of you know that. Let me just remember there is a difference in mathematics. When you say positive, you might see some books write non-negative. Don't think these two words are the same. Yes, when you say positive, it means a strictly greater than 0. When you say non-negative, means it is not negative. So it means that it is either 0 or positive. So non-negative means something like this, yes? Okay, so let us ask the question again. What type of number in general is the norm of any vector? It's a non-negative number, yes? Because it might happen that the length is 0, in which case? Yes? The 0 vector. So the length of the 0 vector is number 0. But any other vector is actually, the length is actually greater than 0. So that is also very good to know. So let me write this. I don't know why. Remark. So the length of any vector is a non-negative real number. Okay, moreover, if someone tells me that I checked the length of this vector is number 0, what can I conclude? I can conclude the vector is the 0 vector. And the other way around. If someone tells me that what is the length of the 0 vector, I will say that this is 0. That's also good to remember. Okay. Now, we want to make a new mathematics on this new concept. So we learned a new concept of vectors. And then if I just define the vectors and don't do anything with them, then they are not very useful. Yes. Okay, but I forgot. Let me also remind you another thing. This is also very important to know. The unit vector is a vector whose length is 1 unit of length, depending in which unit you are working. That's also good to know, okay? So let me write this. A vector whose length is 1 length unit is called a unit vector. Yes? Okay, and then by the way, if you want to denote a unit vector, if U is a unit vector, we usually denote it by instead of putting the arrow, we put something like a hat on it. Okay, so if you see this, of course, I don't know if it is used in your book or not, but these are very important things to remember. If you see this symbol instead of this arrow, it is telling you two things. It is telling you that this quantity is a vector, but because of this hat, this means that this vector is of unit length. Yes? Which way? Here? Here? I will publish these things. So these are digital one. As soon as this is finished, I publish it on Google Classroom. But if you write to understand better, that is of course up to you. You can write. So if I ask you what is the meaning of the unit vector, any vector of unit length is called the unit vector. What is the unit length? It depends in which unit you are working. If you are working with meters, then unit vector is a vector of length equal to 1 unit, yes? The 1 meter. Okay, so assume that you want to construct an algebra. We want to learn how to manipulate vectors. For example, if I just define you a vector and don't do anything with that, of course you learn something, but that is not useful. So why we should introduce the notion of a vector in the first place? We want to use it in some context, yes? For example, you and me are pushing a ball from different sides, okay? So the force that I exert is a vector quantity. The force that you exert is also a vector quantity. We want to see that who will win in this competition. So somehow we want to combine the vector force from my muscles to the vector force from your muscles to see how we can add vectors together somehow. Yes? Of course, this is different from adding two numbers. If I ask you to add 2 and 3, you add them, the answer is 5. But assume that I have a force of 2 units and I have a force with 3 units. Yes? So let me tell you, if I have 2 forces with 2 units, can I imagine a situation that they end up with 0? Yes? With numbers, if I have 2 and a 2, if I add them, they always become 4. Yes? But if I have, for example, pushing against something, you are also pushing with the same force, the same magnitude of force, but in the opposite direction, even though we are using energy of our muscles to push this, but this object will not move at all. So the answer here would be 0, yes, somehow. So we want to learn how to do these algebras using vectors in different directions, yes? Is that clear? Okay, so here, before doing that, if you want to construct an algebra, what is your starting point? So you know there is a quantity called vectors. How many vectors are there? Infinitely many. So we want to start making an algebra for them. What is the starting point first? Yes?
Defining like what you're actually made of, or like how you would write down a vector, if you like wanted to write it down with numbers.
So let me tell you something. When you say 2 plus 3 is equal to 5, so here you know the definition of addition. You say 2 plus 3 is 5. But before that in algebra, you have to be able to define something to make sense. 2 plus 3 is equal to 5. Why does this make sense to you? Because you know the meaning of equality for numbers. Otherwise, if I say that, okay, I add 2 plus 3, this is equal to 5, yes, what is the meaning of this? It means 2 plus 3 is a number, 5 is another number. We are convinced that these two numbers are equal. So we need to understand the meaning of equality before starting setting up the algebra. Yes? So here, we need to know, for example, if I give you 4 over 2, so think about it, 4 over 2, and if I give you 2, you already know that these are two different representations for the same thing, for the same number. Yes, 4 over 2 and 2 are the same. So you put this is equal. So we need to know when vectors are called equal. Yes? So we want to understand when vectors are called equal. So before starting the algebra for vectors, we have to define what do we mean by having two equal vectors. So, and that is probably very natural. If you are a mathematician and you want to define the meaning of equality of two vectors, how do you think you will define it? So I would say that two vectors, for example, I want to test your understanding. If I draw this vector here and I draw this vector, do you think it's a good way do you think it's good to define these two vectors to be equal? It's not probably very good. But what do you think about this? I will take it 2 units, and then I will take this one also 2 units. What do you think? Do you think it's reasonable to define these two vectors equal because both of them are of the same length too? They are not the same direction, exactly. So you see, you are also discovering. So if you are a mathematician, you are already a mathematician. So you told me that it's not a good way to define this to be equal. It's not a good thing to define these to be equal. Yes, because we just told that for vectors we have two properties, two attributes. Yes, one is the length, the other one is the direction. So if you say that I have two equal vectors, what is your expectation? Your expectation is to direction. Yes, so that's very, very natural. So I just want to tell you that this comes very natural. So this we have to define first. So let me write the definition. So I would say that vectors A, let me call it vector U and V is better. Vector U and V are said to be equal. Of course, we write U the same. We use the same symbol of equality. If number one, length of U is equal to the length of V. But this is not enough. The second one is that U is parallel to V. This symbol I am using for parallel. And the third one is that U and V point to the same direction, to the same side, I don't know, point to the same direction. Yes? So of course, some people write these in one. That's up to you. So you understand, two vectors are said to be equal if they have the same length and they have the same directions. If that's the case, we call these two vectors the same. So, and then it is very important to realize the location of the vectors are irrelevant. So it doesn't matter from which point they start and where they end. As far as these three conditions satisfy, then we say that the vectors are equal. Yes, please.
What do you mean by the second one?
This one,
Yes.
they are parallel. So I mean, the lines are parallel means that they are lying on the same plane, but they do not intersect. So might be the last, I don't know, in Persian we have two different words for direction and inclination. I don't know, do you know what's the English word for that? So here, so you see, if I ask you, this is my Apple pen, it points. If I ask you in which direction it is pointing, so of course you say that, I don't know, to which, so if I take it that from your side, it would be to the right. But this line, this vector lies along a line, that is all done, I don't know, this is the English word that I know how to use it, but anyway, so even if these three items is not that clear for you, I can draw pictures for you. For example, I think it would be a good idea if I go to GeoGebra. For example, here, I will take this. This is a vector here. Okay, so the initial point is actually, let me see if I can move them. Move. Yes, this point. Yeah, this point, I don't know, how should I should practice this a little bit myself first. This is geometry in GeoGebra. That's a better application. So this is a vector. The initial point is point A. The final point is point B. Yes? And then if I draw another vector like this, 1, 2, 3, 4, 5 to the right. So hopefully here is good, yes. So are these two vectors equal or not? Yes. Apparently you see both of them are going how many units to the right? 1, 2, 3, 4. Sorry. So I go 1, 2, 3, 4, 5 to the right, 1, 2, 3, 4 up, 1, 2, 3, 4, 5 to the right, 1. So these two vectors are equal vectors. So I am drawing them from different points, The first one starts from point A, ends at point B. The second one starts from point C, ends at point D. But this vector AB is exactly equal to vector CD. Yes? Because they have the same length, they are pointing to the same direction. So these two vectors are equal. Okay. But for example, this vector and that vector, do you think these two vectors are equal? No. Even though they are parallel, even though they have the same length, 3 units, but one of them is pointing upwards, the other one is pointing downwards. So these two vectors are not equal. Yes? So that is clear. So I don't know, this vector from here to here and this vector from here to here. These two vectors have only length in common, but they are not parallel. So these two vectors are not equal. Yes? Is that clear? Yes or no? Okay, let us go back now here. The next step is to define the opposite of a vector. So if you are a mathematician and you want to define the opposite, for example, let us go back to the number algebra. If I ask you what is the opposite of 2, what is your answer? Minus 2. Now we want to have some idea like this. So what is the property of 2 and minus 2? Can you imagine? What is the, when I say what is the opposite to 2, you said minus 2. Why? Can you imagine why? Yes? What is the property of minus 2?
When you combine it or add it with 2,
You end up with nothing. Yes? So the same idea should be in the back of your head if you want to define the opposite of a vector. So I want you to understand, I want you to build up this structure yourself as if you are the mathematician, yes? So what do you think? If I give you a vector, how do you think it would be good if I define the opposite vector? So the idea would be that the opposite of a vector is a vector, so that if I combine them somehow, the effect is nothing. So I push something towards you and you push that thing towards me. For this object to remain still without moving, yes, Sergey?
The opposite would be not the same in the opposite direction.
Yes, that would be exactly the same length, parallel, but in the opposite direction. Yes, because if you imagine the example that I mentioned, you come up with that. So that's a very good thing. So if I tell you what is the opposite of this vector, if I draw a vector here for you, for example, let me call this one vector v. If I ask you draw the vector, opposite vector, by the way, borrowing the symbol from the number algebra, the opposite of a vector is also denoted by minus v. Of course, there is a big difference between the negative for minus 2 and the negative here that we use for negative v. This is a new concept. So do you understand? That negative sign is behind a number. This negative sign is behind the geometric object. It's an arrow, yes? So what is the meaning of the negative of an arrow? We come up with this idea. The negative of v is a vector which is parallel to this vector with the same length but the opposite direction. So if this is vector v, this is also vector minus v. Yes? So this is called the opposite of vector v. Yes, is that understandable? So, and by the way, if I ask you to draw the opposite of this vector, if one of you draw this, is it acceptable or not? Yes or no? That's also acceptable. So you see, because it doesn't matter if you draw it from a different place or you just draw it here. So you can just, if you are lazy enough, if I ask you to draw the negative vector, you can just put the tip of the arrow here, and that would be the negative vector. Yes? So that's understandable. So if I give you a vector And if I ask you what is the negative of that vector, you can draw it. Okay, the next step is how to add two vectors to define the addition, the vector addition. So for example, so let me write this vector addition. Addition of vectors, that's better. Addition of vectors. Okay, addition of vectors, it's better to do it on GeoGebra. So let me go to GeoGebra here, not classic, just go to geometry one here. So what is it doing? I don't understand. Okay, I have to move. Okay, so let us go here. So assume that I give you a vector here, and I give you another vector here. Yes? I want you to add them. This is the definition. I am defining you the addition. So what I am doing, I want to add vector mn to vector op. What you are supposed to do, you have to take the second one and parallel transport it here. Okay, so what I'm saying, you see, if I start moving this vector in this way, all these vectors are equal to the original vector, yes? Because you see, the magnitudes are left the same, the directions are the same, and they are left parallel to the original one. So all these vectors are the same, but this is the rule. For doing that, you take this one, and this is the word that I am using, parallel transported to the end of the other vector. Yes? And then I connect the initial point to this final point. The initial point to the final point. This new vector is the sum of these two vectors. So this is the new operation that I am defining for you. If I give you two vectors and I ask you to add them, this is the way that you have to add them. Is that clear? Yes? So for example, this vector, I have this vector, and for example, I have this vector. I want to add them. So what I do, I don't know if I can copy and paste it. I don't know exactly how should I do it here. Yes, if I want to add these two vectors, what will happen? Again, I will take this vector and parallel. I will take this vector and parallel transport it. I have to get, yes, parallel transport it and put it at the end of this vector. And then what should I do? I need to connect point Q to point T, but I have to put the tip of the arrow at the final point. Yes? So it doesn't draw now, I don't know why. Yeah, but anyway, I can draw another vector. It doesn't matter. I can draw it from here to here. Yes? So this vector is the sum of those two vectors. Yes, is that clear? And I can have more than one vectors, more than two vectors. For example, I can give you a vector from here to here. I can give you another vector from here to here. I can give you another vector from here to here. And I can give you another vector from here to here. And I ask you to add them. So what I'm supposed to do, I have to start. For example, I can keep the first one, MWZ, as it is. I will take this one and put it at the end of this one. I don't know why. Yeah. And then what I do, I will take the second one and put it at the end of the second one. And then I will take this one and put it here. Yes, something like this. And what I am supposed to do, what is my initial point? My very first point is W. My very last point is F1 in GeoGebra. Yes? So I have to connect the first initial point to the final point. and then put the tip of the arrow at that point. So this WF1 is the vector that you are supposed to draw. Yes, is that clear? So if I give you a lot of vectors and I ask you to add them, you add them in this way. Yes. Order, it turns out that the order is irrelevant. Yes, but in principle you should add them in order. Yes, the order that I write down. But the answer, the final answer will be the same. And of course, in principle, I should be able to show it here for you. So let me, for example, go here. I don't know, let me just do some random work here. So I will take this vector from here to here. Yes. And then I have another vector from here to here. And then I will have another vector from here to here, for example. Yes? So let us try to see how this will go. That's a good question, by the way. Okay, so first of all, let me take this one. I add them in this order, okay? So I will take this one and put it here. And then I will take this one and put it here. So what would be the final result? The final result would be this vector. Yes, that would be the final result. Yes, but now let us undo it. So let me remember this vector here. The problem is that this is a little bit hard to, so I don't know, you can remember this a little bit. So let me go back. Okay, so now let me take this one first. It's very sensitive. So let me take this one first and parallel transport it here, and then take this one here. And then what I want to do again, I want to connect this one to that one. Yeah, it's not, so I don't know how to do it right now because I just learned about this new application of geometry in GeoGebra right now. But if you start playing around at home, you see that this vector that I generated right now is the same length and parallel to the previous one. Yes, I don't know. I agree with you that this is not a very nice way of representation. So if I want to represent it for you, let me just do it like this. Okay, so let me draw two types of these vectors. 1, 2, 3. So yeah, let me just try to do this once more for you. Yes, this is one vector. This is also another vector. And this is also another vector. Yes? So now I have two copies of the same thing. Let me now do it again. So I will move this one first and put it here. And then I will take this one and put it at the end. And then what I do, I connect this point to that point. It will generate this vector for me. Now let me just do it once more in a different way. So I will take this one first this time and put it here. And then I will take this one and put it here. And now what I do, I will connect this point to that point. So hopefully you can convince yourself, you can see it in the picture, the vector from G1 to L1 is the same vector as from M1 to P1. Agree? They are parallel, they are of the same magnitude, and they are pointing exactly to the same direction. So what Fria asked is actually right. So it doesn't matter in which order I do it, it ends up with the same vector at the end. Is that clear? Okay, so now this is also good. Okay, now let me ask you some questions. This is just understanding, testing your understanding. Okay, so what do you think will have this one? Minus a vector. What do you think I will have? If I minus a vector 2 times, what will happen to that vector? Yes? No, what is the meaning of positive? It becomes the vector itself. So the opposite of a vector is the vector itself. If I ask you why, you shouldn't say that this is trivial because minus minus 2 is 2. The same reason will tell me that minus minus a vector is the vector. No, you need to imagine that minus minus a vector is the vector itself. Okay, let me ask you another question. If I give you 2 points A and B, and someone writes vector AB, someone writes vector BA, what is the connection between these two vectors, even if you don't know where A and B are? Yes? They are opposite. So then you are learning a new rule. So it means that if you have a vector and you decide to interchange the names, yes, you can do that if you want to, but the price that you have to pay is to put a negative sign behind it. So be careful about that, yes? So that is extremely useful and important property. Okay, let me test your understanding again. I give you 3 points this time, A, B, and C, and I ask you add vector AB to vector BC. To answer this question, do you really need to know where A, B, and C are, or you can just answer it immediately? Yes?
Vector AC,
Why?
because it's
So let me just draw. So you say that I have 3 points. I don't know in which order they are. One of them is called A, the other one is called B, the other one is called C. Vector AB is this vector, and then vector BC is this vector. Oops. Vector BC is this vector. Yes? And if I ask you add vector AB to vector BC, what is the answer according to the rule of combination that we just learned? Is what? Vector AC. So that is a very, I don't know why this works like that, so let me just do it by hand. So this is vector AC. So the answer to this is vector AC, even if you don't have the picture in front of you. So I would say that for let A, B, and C be arbitrary points. Yes, then AB is equal to minus BA as vectors, and AB plus BC is equal to CA. Yes? Yes? Do you have questions? Sorry, AC. Sorry. AC. So these are the good things to know. Yes, for example, can you simplify this for me? AB plus BC plus CA without referring to any picture. So how do you interpret this rule? By the way, this is called Schall's rule. So I think the French name is something like this. I don't remember, but it is pronounced the Schall rule. The Schall rule tells you that if you want to add 2 vectors and you are lucky that these 2 names are the same, it seems that you can drop them and attach the first one to the last one. So remember this rule like this. Now tell me, how can I simplify? Do I need the picture to refer to this? Yes? This is the 0 vector. Why? For example, what you do, you take these 2 according to the Schall's rule. The answer would be A, C. And then you have plus CA. So why? Instead of this one, I have written AC. So this is AC plus CA. Can I use the Schall rule again here? Can I use the Schall rule again here? I don't know why this is moving so much these days. Okay, so this becomes what? AA, but there is a better name for AA, and that is the 0 vector. So you can just simplify this. Yes? Okay, can I simplify this? Can I simplify this? Oh, so you haven't studied, so that's not a good thing to start. So let us talk about that later. Okay. Let me give you an example here in GeoGebra. So what do you think would be the sum of these vectors? If I have this vector, if I have this vector, if I have this vector, and if I have this vector, I ask you to add these four vectors. What is the answer? It's the zero vector, agree? Yes, because they will actually come to the same point, but you need to imagine it a little bit. So you take this vector and draw it from here, you take this vector and draw it from here, you take this vector and draw it from here. So what I am supposed to do, what is the initial point is here, what is the final point is again the same point. So the sum of these four vectors is the zero vector. Yes, is that clear? Okay, now how do you think it is good to define subtraction of vectors? If you want to define a rule for subtracting two vectors, how do you define that rule? What is a good way to define subtraction? For example, do you remember, of course, if I ask you to subtract this, if I ask you to calculate this in numbers, you immediately answer. You answer 1. But there is another way to answer this using addition. Yes? How can I do that? Yes? Yes. So another way is 3 plus minus 2. Yes, the answer is 1. This and this in numbers are equivalent. So let us take this property and define the same thing for vectors. So if I give you two vectors u and v, and if I ask you to subtract them, yes, what I'm supposed to do? Yes, we define it in this way. If I ask you to subtract two vectors, it would tell me that, okay, this is a natural definition. I have inherited this from numbers. So I would say that if I want to subtract two vectors, what I'm supposed to do, I will find the opposite of the other one, but instead of subtracting them, I will add them this time. Yes? So, for example, if I go to a GeoGebra here, so I will give you two vectors. Here I have one vector, and then I have another vector. So I want to subtract the second vector from the first one. So what I'm supposed to do, the first thing that you need to do is to find the opposite of the second vector. But what is the opposite of the second vector? For example, I can draw the opposite of the second vector here. For example, from here to here. Do you agree? What I drew now is actually the opposite of the other vector. So then I will move this vector and put it at the end of this vector. And then what I have to do, I have to add them. So I will add this vector to that vector. So that would be the subtraction of these two vectors. So if you want to subtract two vectors, you need to find the opposite of the second vector and add it to the first vector. So that is the definition of this difference. Okay, any questions? Okay, so let me give you an example here, and then we can stop. You can work on the exercises for this small part yourself. So let me give you this. I have a square here. 1, 2, 3, 4, 5. Yes. So let me just draw it. No. Yes. So assume that this is your square. I want you to show this relation that AC plus BD is equal to AD plus BC. Okay, so this is a good exercise. We want to show that in this square we have this equality. Okay, how we should do that? First of all, this might be a little bit, I want you to understand this is not at the level of the length of these vectors, because what is vector AC? Vector AC is this diagonal. Yes? What is vector BD? Vector BD is the second diagonal. I am asking you to show that if I add this diagonal to this diagonal, it becomes equal to AD plus BC. AD is this one, and BC is this one. First of all, is that understandable? This is not at the level of length. So of course it is clear that the length of a diagonal is longer than the length of a side. But now I am telling you that if you add the diagonals as vectors, it becomes equal to the sum of these two sides as vectors. So why is that? Yes?
Because we don't actually.
Pardon?
I don't know.
Okay. Yes? You mean you want to add something to it? So let me just add that one, yes. Let me change the color. So I will add A to C. This is the same color. So let me change the color. From A to C is here. And then from B to D. A to D. So let me change them with different color. And then B to C. Yes?
So they like you start from the same plane.
Yes?
And they end at the same plane. But the diagonal is longer because it has to travel like sideways as well.
Okay, but intuitively you cannot prove it intuitively. You need to write it mathematically. Okay, this needs a little bit of experience. I want to start from the left-hand side, for example, and do some calculations and see that if this is equal to the right-hand side. If I can show that, then I am done. Okay, so do you agree that AC plus BD is equal to? What can I write instead of AC? You see, on the right-hand side, I want to have AD and BC. But here I do not have them. So it will motivate me, if possible, to write AC and BD in terms of AD and BC. Okay? But can you do it for me here in this picture? Do you agree that instead of AC, I can write AD plus DC? First of all, tell me, do you agree with this one? Can I write AD plus DC instead of AC? Yes? Either you can see the picture, that is right, or you can use the Schall rule. Yes, these two are eliminated, and what is left for me is AC. So AC can be written in this form. Yes? And then what can I write for BD? Can you tell me? More or less similar thing. What can I write for BD? Yes? BC plus CD. Yes? And that is good, by the way. Why? Because what appears here and there are exactly the things that I need, but unfortunately I have an extra piece that I have to deal with. But this is also very easy. So what I do, I add AD and BC together, yes, I can group them, and I can add DC and CD together. But then, what is this one, by the way? The zero vector, not zero, the zero vector. And if I add a vector to the zero vector, what is the answer? Is the same vector. And that is exactly, so that was the left-hand side. I started from the left-hand side, and now this is the right-hand side. Yes? So that is also one good example here that we were able to Yes, is that okay for everyone? Understandable? Yes? Okay, so let me do this one as well, and then we will do it. So let me just try to draw this picture. This is, I want to draw a rectangular cube, if possible. Yeah, something like this. It's not the best picture, but hopefully you understand what I mean. And let me give them names. A, D, X here. And then let me call this one O, B, E, and C. Yes, and here we F. Okay, so I want you to show that FB vector plus BE plus CD is equal to OC. Yes? I want you to show this and this one. OA plus OB plus OC is equal to OX. So consider this rectangular cube and use the geometrical properties of a rectangular cube to show that the sum of these three vectors is equal to OC, and the sum of these three vectors is equal to OX. OX is this diagonal of this rectangular cube, okay? But let us concentrate on this one first. So how we should show that the sum of these three is equal to OC? Let me change my color. So from the left-hand side, there is one part of it that I don't need to even look at the picture. What part? That is the Schall rule, yes? Can you detect the Schall rule somewhere here? Yes? BE. So FB plus BE, that's the Schall rule. So I can eliminate B, and what is left for me is FE. If you don't believe, of course, you can use this. You see, what is FB? FB is this vector, and then BE is this vector. Of course, when I add FB to BE, it is clear that I can get FE. So whenever you can use the Schall rule, I would recommend you to do that. So instead of FB plus BE, I can simply write FE. And then plus CD. Okay, the next I want to wait for you. FE plus CD is no longer a Schall rule, yes, because E and C are not the same. So you see, E and C are not the same. So what is your suggestion now? Then I have to look at the picture. Where is FE? FE is this vector. Where is CD? CD is this vector. How should I add them? I have to parallel transport. Yes, that's a very simple thing to do. What I'm supposed to do, if I want to add these two vectors, I have to parallel transport this vector and draw it from this end of this vector. So but because of the properties of the rectangular cube, it becomes exactly EX. Do you agree? So if instead of CD, if I put EX, that is completely correct. Okay, so what I do, I would write FE plus EX. Why is that? Because EX and CD are equal vectors. Why? They are parallel, because that's a rectangular cube. They are of the same size, yes, and EX is pointing upwards, CD is also pointing upwards. So these two vectors are exactly the same. Understandable? But now, can I use the Schall rule again here? Yes, because now E and E are the same, so I can eliminate them. It becomes Fx. So the sum of these three vectors, I showed that this is equal to Fx. But I am supposed to show that this is equal to OC. But they are the same again, because Fx is this vector. OC is this vector. Do you agree that these two vectors are the same? They are parallel, they are of the same length, they are pointing to the same direction. So Fx is exactly equal to OC, and this is exactly equal to the right-hand side. Yes? Yes, please.
Yeah, but also, I mean, maybe you were going to say that, but I mean, you can also see that FB is the opposite of CD.
FB is the opposite of CD.
Yeah, and if they cancel, they become vector zero over MBE.
That is also completely correct. Thank you. So what Oscar is saying is this. So you have FB, and then you have the last one, CD. Do you agree that these are opposite vectors? They are parallel, they are of the same size, but one of them is pointing down, the other one is pointing up. So if I add two opposite vectors, the answer is the zero vector. So I can eliminate them without spending much more time. So the answer would be BE. But where is BE? BE is this vector. Where is OC? OC is this vector. Again, they are the same thing. So both of them are actually indeed correct. Yes? Okay, so what is the last one? OA plus OB plus OC. We want to show that. Let me now change the color here. So OA is this vector, and OB is this vector, and OC is this vector. We want to show that if we add them up, it becomes the diagonal, this diagonal, OX, of the rectangular cube. So why is that? So you can tell me. I start from the left-hand side and I will follow if you say something. Yes?
This might be an overly complicated way of doing it, but okay, well, if we start off with OA,
Mm-hmm.
and we can, you know that OB, you can see it's the same as AF.
Yes, so let me just follow you. So you want to keep OA, but instead of OB, you want to write AF. That I agree with, because OB is this vector, AF is this vector, they are parallel, they are of the same size, pointing to the same direction, yes? And then let me copy and paste the last one, which is OC. Okay, then how should I continue? Yes, here I have, it becomes OF plus OC, and then what?
And then you can also see that OC is the same as FX.
OC is equal to?
FX.
Yes, exactly. So OF plus FX. So let me describe this one. So OC is this vector, and FX is this vector, but because this is a rectangular cube, they are parallel of the same magnitude, pointing to the same direction. And again, you can use what? The Schall rule, yes? So it becomes OX. And this is equal to the right-hand side, yes? So now you learn actually how to more or less do something with vectors. Addition. So we learned the concept of a vector, the concept of a scalar. We learned how to determine the opposite of a vector. We learned how to add vectors, and we learned how to subtract vectors. I haven't. Yeah, I think it's a good point to stop here, and I will write on Google Classroom which part of the book you have to do for this part. Okay. Okay. So, any questions? No? Okay, I will stop this here.